Okay, so here is another table method problem. This is an equilibrium problem. And we have this plate that weighs 100 pounds. It's suspended by 3 strings. And we want to find out the tension in those strings. All right, so first of all, let's define some axes. I'll say that's x-axis and this is the y-axis. That makes the z-axis going up through string B there. And then let's find out, let's determine some shapes. I'm going to divide this up into 2 subshapes. I'll call this subshape 1 and this one number 2. And then we need to find the centroid of each of those subshapes. So I'll put that'll be the centroid of that shape, which is also the center of gravity of that sub-weight. And then this will be the centroid of that one. All right, so let's build our table. So I have 1 and 2 and x tilde, y tilde, area. X tilde area, y tilde area. Now, why am I using areas? I know I can calculate areas from the geometry of the picture, and I think that that'll work fine. I could use weights or masses, except that I know the weight of the total thing, but I don't know the weight of each individual part. So that'll be hard to separate this up into weights or masses, but easy to do in terms of shape. So let's do it that way. All right, first of all, x for part number 1. Here's the centroid. It is halfway, it's a rectangle, so it's halfway this way. So that's going to be 2 feet, and it will be half this way. So it'll be 1 in the x direction, 0.5 in the y direction. The area is 1 by 2, so that'd be 2. So multiplying that out, you get that. All right, shape number 2 is a triangle. The centroid of a triangle is 1/3 from this side. It is dimension 2, or 2 feet this way, so this is going to be 2/3 in the x direction, or 1/3 of 2. Same thing. In the y direction, I go 1 plus, again, 1/3 of 2, so 1 and 2/3. The area here is 1/2 BH, so it's a 2 by 2 is 4, divided by 2 is 2. All right, multiplying these out, I got 1.33. This is 3.33. All right, adding those together. 4, 3.33, and 4.33. Finding my x bar, it is the, x bar is the sum of x tilde area over the sum of the area. So that's equal to 3.33 over 4, which is equal to 0.833. And y bar is going to be equal to 4.33 over 4, which is equal to 1.083. All right, and those are feet. I guess that's what we're doing. All right, how do I find the tension? Fairly simply, actually. Now that I know the location of the center of gravity of the structure, I can, in fact, let's draw it on the picture. I'm going to say that the center of gravity of the structure is kind of right out in here. And it has a lever arm in this direction of y bar and this dimension of x bar, which I've just calculated. And if I want to know the tension, let me scooch this up here a little bit. Let me zoom out. I can say that I can sum the moments about the x-axis is equal to 0. So in this case, I have minus the weight times y bar plus c times, in this case, it is 3. This is the total dimension here. So I can find out the tension in C. The weight is 100 pounds, and C then is going to be equal to 36.1 pounds. I can sum the moments about the y-axis to find A. And you find A then is equal to 41.65. And then I could sum the forces in the z to find the last one of B. And you can find B is equal to 22.24. So I didn't solve those completely for you. You can do the math and make sure that you know how to do that, but the process should be pretty easy. No, I don't know about easy. I never want to say things are easy. They're always easier for me than they are for you. But what I mean is that they should be straightforward, because we have been doing a lot of moment about an axis kind of problems, and so this is just another example of what we need to be able to do. All right, this next problem is already done for you, but it's another example of finding the center of gravity, and in this case, it is another two-dimensional problem and solving for a reaction. So I'm just going to walk through here with you, or walk through it with you. So here's kind of a randomly shaped weird thing. It's got a little disc over here that has a mass of 6 kilograms. Just move that down just a little bit. And then the bars each are distributed. It says that they have a mass of 2 kilograms per meter. If I want to find out the center of gravity of this total shape, it's going to be above this axis. I know that it's above this axis because it's got this part going up. Where in this direction might it be? It's hard to know, but feels like this has a lot more mass out this way. So I'm going to guess it's going to be probably over here someplace, a little above this axis, but heavily weighted on this side. So appropriate thing to do is define a location of 0. And so in this case, I'm going to define this as 0 right there. So this will be negative going in this direction, negative. This is positive x. And then, of course, this is positive y. All right, let's just walk through the pieces then. Let me talk about the pieces. I'm going to call this piece 1, this one piece 2, 3, and 4. Okay, with that, all we have to do is just kind of fill in the table method, or fill in the table for the table method. For 1, I have x bar. It is in the negative 1. So the center of gravity is 8 plus 0.2. So that is negative 1. It's in the x-axis, it is 0. It has a mass of 6. And you can multiply it out. Number 2 here, this is 8.8. The center of gravity is right there, which is 0.4. Again, the x bar is going to be the center of gravity of the piece. So negative 0.4. It's still 0 in the y bar, or in the y-axis. This weighs 2, or has a mass of 2 kilograms per meter times 8.8 meters. That gives us 1.6 kilograms of mass, and multiplying that. These are both in the negative x direction, so they have negative distance. And then when you multiply out, you get a negative product. In the positive axis, we have this is 2 kilograms times 0.5 meters, so that is 1 kilogram of mass. Center of gravity is 0.25 in the x and 0 in the y. And then this one is 1.1 meters. So in the vertical direction, 1.1 divided by 2 is going to be 0.55. In the x direction, it is 0.5. In the x direction, the mass is 2.2, and multiplying those out. So again, you've done this before several times. Sum the masses, sum all the products, and you get x bar and y bar is that. So then if you draw a free body diagram to try to find the reactions, you can kind of just keep this side of the shape, draw the reactions. You got an AY, you got a BY, you got a center of gravity, which is located 0.49 from this direction. Sum the moments about B, you can find AY. AY times 1 minus mg times 0.490, that's equal to 0. Should have put that equals 0. Sorry about the red. Find AY doing that. Sum the forces in the Y, and you can find BY. All right, this last problem is I'm not going to do this one for you. I just wanted to point it out as a good homework problem. But at any rate, the concrete barriers have a predictable shape. They all kind of look pretty similar to this, but you have to break this up into quite a few different pieces, different triangles and rectangles, all having their own little centroid and all having a distance from the base here, the x-axis. It's going to be uniform around the y-axis, so there is not going to be any x-bar that you have to worry about. But the y-bar is coming up from the y-axis. You should expect that there's going to be a centroid of that weight up some distance from the base. Then our calculation here is how much force does it take to push it over. So it's kind of an interesting little trigonometry problem and centroid center of gravity problem.